Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am super happy to have Matija Ćuk with us today. Hello, Matija.
Hello.
Let's see. It is August 30th of 2024 as we record this. And what's your geolocation there, Matija?
Mountain View, California.
Mountain View. Lovely, lovely, lovely. So it's California. It's in the Bay Area. And is fall started yet? Is fall started to tweak over?
No, it's still pretty warm.
Okay. We're definitely still, I'm in Phoenix. We're definitely still warm in Phoenix. We definitely hit the triple digits today, 105F or something like that this afternoon. But it is starting to cool off. It's been about 10 degrees cooler in the morning. So I'm keeping my fingers crossed that we cool off nicely here soon. So very cool. And Matija, what do you like to do for research?
So I'm a theorist and I do orbital dynamics usually.
Awesome.
But then it gets involved with formation and evolution of stuff, usually satellites or asteroids.
Very cool. Very cool. And that is going to bring us to this very awesome PSJ article. It is open access. It's the open access era, people. Go grab a copy for free. BYORP and Dissipation and Binary Asteroids, Lessons from DART. And Matija, take us away.
Yeah, so first I would like to have a shout out to all the co-authors. I'm going to read everybody. This has more co-authors than any paper I had so far.
Okay.
Because these are people who are on the Dynamics Working Group for the DART mission.
Okay.
Mm-hmm. So this is a mission adjacent paper because I was not part of the mission in terms of funding, but I had a separate funding for science that was very similar to what came out of the DART spacecraft.
Cool.
Mission. The curiosity is that the mission itself was run by a different division and was not technically a science mission, but my funding was for science. Yeah. And all of these folks contributed to the whole community, like trying to make sense of what we saw during the mission.
Right.
So I guess first I'll just remind people what DART was. So about 2 years ago, DART spacecraft impacted the satellite of asteroid Dissipation. Mm-hmm. Satellite was called Dimorphos, and this was done so that we would test if a kinetic impactor, a spacecraft, can change the orbit of an asteroid. And this was kind of an easy case because satellite was small and was moving slowly. So we got a good result, and you can read up all of that on the other papers about DART mission. But since I studied these small binary asteroids for a living, I wanted to make sense of what this experiment tells us about their science. Cool. And so what do I mean by small binary asteroids? They're about 15% of near-Earth asteroids and probably small asteroids in the asteroid belt are binaries in which the primary is top-shaped. You've seen pictures of all of these things, and even some singles look like that.
Yeah.
And then the secondary is usually more elongated and is almost always spinning synchronously with the long axis towards primary.
Mm-hmm.
Yes. This is really a, kind of a uniform, most uniform class of systems. I've been working for them for a long time, and their dynamics is extremely interesting. We think that the primary spins up through radiation forces. There is the radiation effect called BYORP that makes things spin up. Yes. And the primary might lose material from the equator and form the secondary. That's hand waving, but that's pretty much how we think they form. And then once the secondary is in orbit, you got both tidal forces to the primary and radiation forces acting on it. And those two sometimes act against each other. And we are trying to figure out what the life cycle and dynamical behavior of the binary asteroids is.
Yes.
How long they live and how they start, how they end.
Cool.
And the DART mission was our first close-up view with a spacecraft of a small binary asteroid.
Yeah, it was really awesome. Mm-hmm.
Yeah. So that's it for the intro. This is the point where I would like to show some pictures, maybe.
Yeah, let's take a look at some of those. So I'm going to stop sharing people, and we're going to do a little slides, a few slides.
Yeah. Okay, let me see. Okay.
There we go.
Yeah. So first, what is this BYORP thing that is in the title?
Yes.
And stands for Binary Yarkovsky O'Keefe Radzievsky Paddock effect.
Oh, you did
So
that well. Very good.
without B, it makes single asteroids spin up or spin down.
Yes.
And this is the variant of it that affects binary asteroids. So here is very schematic. You have a primary, and then you have a little satellite that is in synchronous rotation, which means that it has a permanent leading and trailing hemisphere.
Yes.
It's not really a hemisphere because it's it's potato shaped.
Not spherical.
And then,
upper half, lower half.
yeah, it has the same silhouette. So incoming
Correct.
sunlight, this thing is orbiting the primary, and then primary is going around the sun. So sunlight on average comes from a random direction, comes from everywhere.
Okay.
But the way the infrared light is being re-radiated is not random, because the surface is misshapen.
Yes.
And the front that goes forward is different.
Oops. Okay. Hopefully it comes back.
So therefore, this is the BYORP effect that is in the title, and the fate of the satellite's orbit depends a lot on this surface shape.
Yes.
And this is relatively major effect. Like, it can be as fast as 30,000 years in collapsing the orbit or making it expand.
Okay, cool.
So how do these things look like? Well, first, let's look at the single asteroids. This is Itokawa, some kilometer near Earth asteroid. You can see it's nothing like round. Actually has multiple parts, which seems to have some strength. And when you calculate the radiation forces on Itokawa, it depends a lot of what the angle between the two pieces is, really, that seem to be stuck to each other. So you move one a little bit, everything changes. So that's the main contribution to radiation forces, not little boulders on the surface, but how the two big pieces are arranged.
Right, radiating surfaces.
So the past, when we tried modeling binary, asteroids in general, we had artificial shapes like this. You can have a computer generate shapes according to some recipe, and we try to have them have large, bulgy parts coming out, and the overall shape determines the response to radiation forces, usually.
Yes.
But then this is Didymos from DART, just before it hit. This is like seconds before it hit. And you can see the overall shape is quite ellipsoidal, looks like a football. Now, there are large surface. Part of it is that Dimorphos itself is very small. It's a couple hundred meters across.
Yeah. Cool.
Does not have large components. It just could be one big pile of rubble that's in some kind of hydrostatic shape, relatively speaking. So this changes how we calculate this BYORP effect.
Okay.
And now it's time to go back to the paper, I think.
Okay. We will go back to the article, and we will go down to figure 1, I believe.
Yeah, figure 1 would be good.
Figure 1, there we go. Ellipsoidals.
Yeah. So now we have to have a new model. These potatoes are no good, so we need spiky footballs. And so we make some assumptions. We can make an assumption that the unevenness of the surface, which depends on boulders, is independent on the overall size of the secondary. That boulders are always the same size.
Okay. Okay.
So that if a secondary is like kilometer across or 200 meters across, boulders are going to be 10, 15 meters across. And then, but then when you make a plot, when in which radius of the secondary is 1, then it looks like boulders have shrunk if the secondary itself is bigger. So these are some artificial shapes that have different amount of unevenness on the surface. we have this bunch of triangular facets. It's subdivision of icosahedron, if you need to know.
Good.
It works
Yes,
better than a spherical grid.
yes.
And in all of these models, I just toyed with how much off surface different points are, and you get this triangular facet that stick out. And then we calculate how it irradiates light.
Okay. Good.
Yeah, and general drift is that since the surface unevenness depends on the size of the boulders, which is fixed, bigger the satellite is, less of an effect the boulders have, because they cancel out.
Yep, I'm with you.
Okay, so I think we can go to the next figure then.
Slide on down, figure 1, figure 2, distribution.
Yeah, so we show what the scatter is depending on the size, and basically more facets you have, less of a scatter in radiation properties there is. So this basically shows on the x-axis shows the how much acceleration you get from the unevenness, right? Radiating light.
Yes.
If you have more facets, which are the two skinnier curves, it just means that you're closer to zero. And if you had an infinite number of facets, there would be no effect because you're smooth. That's
Fair enough. Fair enough. Yes. Okay.
So then let's go to the next plot.
Okay. Yeah. All right. Very good. Figure 2. Let's slide down to dispersions.
Yeah, so we are trying to figure out, depending on the size of the boulder, to do a dispersion of the this force, radiation force, and radiation force on average is 0. So how much it is different from 0 depends on the dispersion of the whole distribution. So we are assuming that the measured forces on real asteroids are on the order of dispersion of our artificial population.
Okay.
So yeah, so I guess I should say here that the change of the orbit has been measured in 4 different binary asteroids, including Didymos.
Cool.
And in some it's large, in some it's small, and it's really hard to tell why is that so. And it turns out that it's actually one asteroid in which it is large, binary asteroid in which the migration is large, is actually has a very small secondary. So it would make sense that it's rough on the surface and you get more of an effect. And the 2 binaries in which the drift is smaller actually have large secondaries. So it's all so that kind of fits to some extent. Yeah, well, makes sense.
Yeah. Okay.
Yeah, so we can go to the next
Ooh, there we
so
go.
yeah, now we plot our predictions. That we are basically saying that larger, so relatively smaller the boulders are compared to the whole moon, you get less of this BYORP parameter, which is basically a radiation force. So this is the small end, small boulder end, which is big secondary end you're showing. And then on the opposite diagonal part end is the when the secondary is small, boulders are comparatively large, and you get a large effect. So the 2001 SL9 is an asteroid that has very fast migration.
Yes,
now,
it certainly did.
Below the line itself. And so what we are saying is the dispersion, you can have something much closer to 0 than the mean width. It just depends where where you hit it.
Yes. Okay.
Yeah, where you hit the distribution. But in general, that would explain why for example, 1999 FG3 has much slower migration than 2001 SL9. So
that ratio.
So far, we weren't sure why we get such different results from measured migration. People thought that it might be tides mixed in with BYORP effect, that it could be of the same order, magnitude, but that causes some other problems that are too complex to go into.
Okay. Let that one go.
Maybe we can all explain everything with the radiation forces.
Yeah, that would, well, that would help. That would be cool. Okay.
Yeah.
All right.
So that was the first part of the paper. that try to see how what we saw at Didymos, how it changes how we think of radiation forces on secondaries in binary asteroids. That's the BYORP part.
Okay.
And the second part of the paper is about dissipation.
Okay.
And I don't call it tides, but dissipation to be more general.
Yeah, a
because,
lot of it.
Yeah, there is lots of math here. There are not many figures. I'll make a mention that I did lots of use of recent work by Tony Dobrovolskis, who unfortunately passed away last year, who was real giant in the field. So what motivated the second part of the paper is that when we saw Dimorphos, it's not clear from the picture I showed you, it looks like a football. It's actually more like a bean, like a flattened sphere.
Yes. Okay.
It's not actually elongated. Yeah. On average, these satellites are footballs. Most of them are elongated, but Dimorphos, when they put pictures from different angles, turns out to have two axes, big axes, they're almost the same, and the polar axis that is shorter.
Yes.
And it's not supposed to do that. Now, why it's not supposed to do that? Because energetically, it's better to be football shaped. And then the tides from the primary kind of lock to that shape, and that's a lower gravity configuration than having something that's symmetric, rotationally symmetric.
Okay, I'm with you.
And in observations from the after the impact, people have detected that the orbital precession, which is shifting of the orbit due to the non-spherical gravity field of the two components, does not match what they expect with the pre-impact shape. So after lots of math, you can figure out that after the impact, Didymos is elongated. Dimorphos, the moon, is elongated and football shaped. The primary did not change shape because it was the secondary that was impacted.
That's it. Yeah.
So it's not just that it made a hole and that changed the shape. Like the whole thing seems to have reshaped after the impact.
Cool.
And you can see why, because if that's the more energetically stable configuration, you whack it and it settles into a lower energy state. So it's a little bit like having unstable cliff. You have it's prone to landslides, right? And then things flatten out as the as the gravity wants to do. So I did lots of math doing the energy budgets, but basic idea is that there are different modes of behavior of these small asteroids, that most of the time they are behaving as rigid bodies. So you can have things that are not in most stable energy states because the material strength keeps them in certain shape. But then once you whack them hard enough, and how hard it is, it's not clear, they behave more like fluids. And they follow the what gravity wants them to do more closely. And reshape.
So like a granular flow.
Exactly. And I mean, I'm more of a theorist. People have worked way more on this kind of stuff, but it's more than I'm saying that so much of dissipation on binary asteroids happens in the very short times when conditions are different than usual. So you have most of the time they are frozen in, their shapes are frozen, and the behavioral rigid bodies have their oscillations, precessions, nutations, all these things that dynamicists love to do with rigid bodies. But then now and then they reshape, and during that time they also dissipate energy. So you get things like damping down of rocking, of non-principal rotation, of eccentricity. And that's interesting because most of the systems we are seeing have the secondaries in principal axis rotation. That means that they're not wobbling, they're just spinning around a single axis. Also, the secondaries are always facing the primary. That means that they're in synchronous rotation. With one side is facing the primary, the other one away. And also the orbits are close to circular. So these are all things that you expect to happen when there is dissipation. And radiation forces cannot do all that because they don't care about lowest energy state. So I'm arguing that all of that happens quickly. And then over the millions of years, or well, I don't know, it's millions, but over long periods of time, then the systems behave more or less rigidly and accumulate excitation from other forces, including radiation forces, and then occasionally go through these periods of high dissipation.
Right, rapid.
And like what we caused artificially with DART, but might be caused naturally either by collisions or just when the gravitational forces overcome certain amount of material strength and everything, like there's a landslide, basically.
Yes, 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 yes. Very much like a glitch on a neutron star.
Yeah. Yeah, so that's the purpose of this chapter. I'm going into the details here, but there is really no reason to
All good.
to discuss the that really surprised me in this researching this is that it's not easy to calculate the self-gravity of ellipsoids. It's if it's triaxial, it cannot be done analytically, apparently.
Yeah, sure.
Yeah,
especially rough ones.
Okay, so we come to the table.
Yeah, let's take a look at this one. This is cool.
Yeah, so look at the middle figure, because there are two alternate estimates depending on different ideas of what happened afterwards. They're somewhat similar, but not identical. So the energy of the impact dumped was positive, obviously, and lots of energy was dumped on Dimorphos, but actually after the dust settled, literally, it ended up having less energy than before, and you can see all the other terms are negative.
Yeah.
Yeah, so the energy of the impact was carried away mostly by ejecta and was not really absorbed by the body. And and all of these things just happened to go downhill energetically because they were triggered by the impact, but actually use their own energy of the shape, binding energy, and so on to
16%
to settle into a lower state.
Yeah.
Yeah. So
very.
I guess I just had to do the math to show that actually, yes, all of these changes are energetically favorable.
Yeah. Nice. Very good. Okay.
Yeah. And the last one is about eccentricity. So that brings us to the predictions.
Ooh,
so it's not completely clear how eccentric the binary is now. That is how eccentric the mutual orbit of the two components is, and how non-synchronous the rotation is. Is the Dimorphos always keeping the same side towards the Didymos, or is it rocking back and forth a bit, or more than a bit?
Yes, libation. Yes.
So on average, it has to be synchronous just because of the behavior of the orbit, as I said, the precession of the orbit. But there are big error bars. So Hera mission is going to visit Didymos in a couple of years, and
cool.
It's going to orbit the system and observe Didymos and Dimorphos.
Nice.
And the question is how excited or damped the system will be at that point.
Yes. So
we are placing bets, kind of.
Ooh.
And most people think that it's going to be relatively excited.
Okay.
So what you highlighted is work by Rachel Cueva, who shows that regular tides should not do much in a couple of years, which makes sense. Tides act onto thousands or millions of years. But this thing I'm talking about, that kind of
perturbation,
granular flow and so on, might be able to damp the eccentricity, like maybe already have. Actually, Didymos moved away from Earth. We don't know what's going on right now. So my bet is actually there'll be more dissipation than people expect. And the thing will be in more orderly shape.
Okay. Okay.
That the rotation will be more synchronous and the orbit will be more eccentric than it looked like after the first post-impact.
Initial bang, right.
Orbits,
so settle down. Okay. Okay. What are the odds on that? What does it pay?
Oh, I'm not putting any money on it. But it's good to distribute, that some people say one thing, the other people say the other. Unless it's something third, somebody's going to be right.
Very interesting to see. Yeah. Very cool.
So go through some implication for the, this is good to figure. For the larger for the larger picture of binary asteroids. And then if we can explain all of the observed orbital evolution. So on the y-axis, we have orbital evolution, on the x-axis size of the asteroid. So the tides and radiation forces have an opposite dependence on size.
Nice.
Tides are stronger for larger bodies.
Yes. Yes.
And because the gravity is stronger and defeats material forces, but for smaller bodies, they have more surface area for their volume and mass, so radiation forces are relatively stronger. So if the observed time evolution timescales, tidal evolution time, well, not tidal evolution, the orbital evolution timescales are due to radiation alone, then tides can be below the level of what we are seeing.
Okay.
For the size range we are looking at. So you can see when you go to larger binary asteroids, then tides will dominate.
Okay.
Yeah, so the color here means
Okay.
of the lines is how large a secondary is.
Yes.
So the light blue is a large secondary, magenta is a small secondary. You can see for radiation forces, small secondaries get affected more because they're smaller. Right. And for the tides, it's the large secondaries that are affected more because they're more extended.
Yes.
And the gravity of the primary can affect them more.
Nice.
So if everything we are observing here is due to radiation forces, then tides can stay down below that, at least for this size range, sub-kilometer size range that we are working at.
Yes.
And then we don't have to have tides and radiation forces balance each other, as that's a popular proposal by my co-author Seth Jacobson, that all the systems we are saying are in balance, and I don't like that because, as you can see, the size dependence of the two kinds of forces makes it hard to balance them across the range of sizes and shapes. Now, the proposal, he also proposes the tides don't work the way we think, but maybe if everything we see is radiation forces, we can get away from having to mess with tides too much.
Sure about it. Yeah. Especially on shorter timescales. Cool.
Yeah, it's hard. Some of these things are not very old. This is a population that just keeps being made and lost probably all the time.
Good.
Okay, so I think that's most of it.
Yeah.
So I'm just saying again that we think that the shapes are more ellipsoidal than we thought, and that the dissipation happens in short bursts rather than uniformly over long periods in binary asteroids. And both ideas are inspired by what we saw at Didymos.
Very nice. Very cool. Matija, I want to thank you so much for walking us through your very awesome article.
Thanks.
Sure. Let's see. And you touched on I'm echoing. A couple of points there that I wanted to push on a little bit. And so where do you think we go given the published article? What would it take to get a better shape? What's the time scale for the Hera mission? And are there...
Oh, I should know that, and I don't, but it's like 2026, I think.
Oh, that's relatively recent.
Okay. It's really soon, yeah.
Oh, okay. Okay, very good. So what are the next steps? Let's say Hera goes up, get something. What do we do?
Well, we'll see if, first what the new shape of the Dimorphos is, and also how excited it is or not. So this is as close to experiment as you get in planetary science.
Nice.
On one hand, it's nice that we get to study a binary asteroid, but first time I heard about the mission, I thought it was so sad that we have a perfectly good binary asteroid and then we are messing with it.
We're gonna kick it a little bit, 16% kick.
Yeah.
Such is life in experiments.
Yeah.
It's all good. Very good. Well, it'd be really exciting to see this field develop over the next couple of years. And
yeah, this field is excellent. Like I remember 20-ish years ago, it started with the radar pictures from Arecibo. Unfortunately, we don't have Arecibo anymore.
Right.
We were hoping to get some flybys of other binary asteroids by small spacecraft. They were supposed to piggyback on Psyche. That didn't happen because of the launch delays, but maybe with lots of smaller launches these days, eventually we'll get to see more of these things close by.
Nice. It'd be really cool. Very nice. All right, Matija, thank you so much.
Thank you.
And that will do, everyone. And I hope this made your astronomy day, your binary asteroid day, just a little bit better. And we will see you on the next one. Bye-bye.